My name is Igor Reinares. I work for LAULAGUN Bearings. In LAULAGUN, we design and manufacture and test big bearings for the wind energy sector. This spiel is to talk about the challenges in the blade bearings field, more related to the data-driven maintenance strategies. Well, nowadays we can face different scenarios or situations. In our case, we can summarize that in 4 main points. From the sensorization point of view, comparing to the main bearing, where normally an accelerometer or temperature sensors are integrated, the pitch bearings are not enough sensorized. Of course, hydraulic and electric systems are monitored continuously, but there are not enough sensors originally in this type of components. Also, the current indicators or pitch-related alarms that we could receive from the SCADA system could rely on a late detection of a specific failure mode. And of course, a failure in the pitch system has a big influence in the performance of the wind turbine, especially from the power production point of view. In the case of having a big damage on the blade bearing, the cost of replacing it is quite big, especially because you need to stop the wind turbine for some days, and also because the machinery involved in the tasks is very complex and very costly, so the consequences are very big. Then we can select 2 main challenges in this field. As I said before, it is not that easy to detect incipient failure modes within the current sensoring system, but that could be improved by testing new techniques, using additional sensors, and deploying new tools, like, for example, algorithms for specific failure modes. Basically, the aim in this field is to optimize maintenance works and improve planning activities by understanding better the health of the blade bearings, if they have any damage or not, and in case they have it, how long are they able then to keep working without any big influence in the performance of the wind turbine. So to deal with all those challenges, we have been working in the development of the following technology within the ROMEO project. We mainly focus in 2 general failure modes, rolling contact fatigue and structural health monitoring. We have developed a new diagnosis and prognosis algorithms. From the hardware point of view, we have been working with our condition monitoring system. And what we did is the following strategy: design and configure the system to use it with the selected sensors and the required sampling and data management strategy. Also implement the algorithms, the 2 that I have mentioned before, and check if they can be executed properly. And finally, we perform a long test in a real scale test bench, where we have implement and validate those algorithms. Regarding the work related to the damage calculation methodology, in this diagramming, it can be shown how the algorithm works. We mainly have 2 types of inputs. From one side, we have control data, which basically are the applied measured loads and pitch values plus the data from the strain gauges. Apart from strain gauge, it could be more type of sensors if they are considered with the algorithm. And from the other side, we have our own calculation methodology together with a finite element model. Combining these 2 sources of information, the methodology obtains the equivalent contact loads, then the equivalent axial load and the capacity of the bearing considering the geometry of it. So finally, what we get is the remaining life of the bearing in cycles. And with that, we can calculate the generated damage of the bearing in the time domain. Finally, to resume the work of the field, we divided the work in 3 main subtasks. The first one would be the implementation, where we implement for first time our algorithms in our condition monitoring system within a long test carried out in a real-scale test bench. The second phase would be the validation, where after some debuggings and corrections of the algorithms, a new test was launched. In this phase, we could validate the results and the generated damage together with the remaining useful life. Also, the results correlation has been done by doing a post-mortem analysis of each blade bearing after each test. And finally, we developed a portability report where we define all the requirements to port the system successfully to another subsystem. So to sum up, two main conclusions: we have achieved good results to continue working in the field of the diagnosis and prognosis algorithms, and we have improved our criteria to continue researching and validating the developed algorithms in the future. This is the end of this training build. Thank you very much for your attention.